All right, let's go with it. 8.4. So we were introduced to this something called exponential functions in 8.1, if you guys remember. We looked at the graph of them. We looked at some computation with them. And then we went to 8.2, and then we looked sort of almost like took a break, right? We talked about something called inverse function. How do you go from one function that does the exact opposite? If you add 2, this function will subtract 2. If you multiply by 2, it divides by 2. So it undoes the work. And that took us to 8.3, which we looked at something called logarithmic functions. Bless you. And we figured out that logarithmic functions are the exact inverse of exponential functions. Where the exponential function calculates the value, the logarithmic functions calculates the exponent. So they work backwards with each other. Okay. And then we looked at just a couple of properties. And let me see if I can maybe just go back before we begin this. Because we'll probably need that. 2 properties. Let me just go back just quickly here on a few slides back. I think we looked at this one here. Remember this one? If you put a base and the log goes into the exponent, and it's the same base right here, the bases cancel each other out. And the quick example that we use is this one right here. So log 5, base 5 to the exponent of log base 5 to the 25, this becomes really 2, and then you get 25 again. And then there was a sneaky one last time where I said, you know what, what's this one? It's just 34, because the property is still going to hold. You don't need to calculate this in order to get that answer. And so the general formula. And then then it was this one right here. What happens here if you have the same base to the log and the base inside the number? What happens? You can really technically just cross these out as well, because if you start calculating things out, you get 125 for this one, and then what exponent you put on 5 to give you 125 is going to be 3 again. So again, forgetting the whole process, but just knowing the formula, we go from here, and we should get an answer of just 28. Is that right? So we find out this here. If I put a log with that same base to the exponent, really, that's just going to cross out. It leaves you with that exponent only. All right, so now we jump to 8.4. We're going to add quite a bit more properties now to this, to the point that your 3x5 card probably will be filled just with the properties here. All right, so let's start off. Last time we were looking at earthquakes, Richter scale earthquakes. I think we finished off with that. A Richter scale of an earthquake, I should say that. We're going to change to another application, something called decibel scale, how loud things are. And so here's a light whisper, would be considered a 10 in the decibel scale. And then you go on from here. Think about it, it's almost like the Richter scale, right? We sort of scale things to go a certain height here. So noisy office would be 60, rock music, subway, 80. I remember, date me a little bit here, but I remember the early 90s, maybe even late 80s, but early 90s. There was no cruising in Fresno. There's a Blackstone Avenue where you had these just wave of cars that would go up Blackstone Avenue, come back to Blackstone Avenue, go up. And of course, the music got louder and louder progressively each evening. So Fresno had to institute a decibel noise limit rule. And so the cops were out there with their decibel meters, and they would go next to a car, and if I think it was 60, I want to say it was 60. If it was beyond 60, or maybe 80, maybe it was right on. If the officer with its decibel scale, if it went above 80, you got ticketed for disturbing the peace. So, and that is based upon the decibel scale here. All right. Again, in a graph sort of way, there it is. But we want to look at a formula. What formula makes this happen? That's the question. So the precise definition for decibel, as far as a calculation goes, it's 10 multiplied by the log base 10, and then there's this little division right here. I is the intensity of the sound, and IO, or sometimes called I naught, K-N-O-T, it means the smallest little tiny thing that we can measure of noise with what we're using here. And so this section says is this formula right here, it can actually also be written as this formula here. So the rules we have, we can rewrite formulas from a division of things to a subtraction of things using logs. And maybe hopefully we'll make that connection when we do this here. Okay, so again, a whole bunch of properties coming your way. So property number 1, and this whole section is just about properties. All right, and I'm going to go just a little bit faster just so we can finish by break. That's my goal here. All right, again, let's look at an example here first. So log base 2 of 32 is equal to 5. Tell me if you guys agree first. I think so, right? That's true. What exponent do you put on 2 to give you 32? That's going to be 5. So what I'm going to do, I'm going to break up this 5. I'm sorry, break up the 32 into products of 32. Let's see. 32 could be 4 times 8. Would that work? 4 times 8 is 32. So how about if we do this one here? Log base 2 of 4 plus log base 2 of 8. Question is, what will that give me? And again, these are just sort of illustrations of the concept. All right, let's see. What exponent do you put on 2 to give you a 4? 2. What exponent do you put on 2 to give you an 8? And well, hey, look at that. That's interesting. Look at that. 5 is here. 5 is there. So that means if this is equal to 5 and this is equal to 5, that means this and this are the same. Okay, again, this is just an illustration, right? It could be that the numbers just sort of worked out that way. So we have to look at it as inductive process here. We just say, okay, how about if we just try a whole bunch of different numbers? We'll still work for a whole bunch of different numbers. Anyways, what exponent do you put on 5 to give you 125? 3 is good. And so let's break up that 125 into 2 multiples. How about 5 and 25? Yeah, cool. So how about this? Let's go with log base 5 of 25 plus log base 5 of 5. Alright, let's see. Exponent you put on 5 to give you 25. 2 is good. Exponent you put on 5 to give you 5. Just a 1. Hey, look at that. Adds up to 3 again. So again, we could try a whole bunch of numbers. This would be more like the pre-algebra method of doing this. It just sort of verifies just to see if it's going to work for 1,000 numbers. Alright, but in proper mathematics, what we do is we try to, again, I'm going to show you this here, not part of the class. This is extra. It's a freebie. Again, also not going to charge you for it, okay? I'm going to produce a little proof. Let's see if this makes sense. That's why I went to those properties earlier here. Anybody remember anything that looks like this? What would this equal? Yeah, base, right? Log in the base. This guy has to equal an xy. If that's true, everybody good that's true? Okay, here's a little extra step. This comes from Algebra 2 in high school here. If this is true, can I put this in? I'm going to put it in separately then. Since these are multiples of each other, right? These are just products of each other. See if this makes sense. Base to the log of base of x times base to the log of base of y. Can I do that? Yeah. If it cancels off, I can put them together. And since these are products, I look at the x individually, I look at the y individually, and I make 2 groupings like that. And then I have something called exponent rules. If I have 2 things with the same base and I want to multiply them together, what do I have to do with the exponents? This is going to be b to the exponent of log base b of x plus log base b of y. Voila. Did I just prove something? I proved that the whole entire left side is equal to the right side. And in that case, I just proved, the little dot means therefore, this exponent and that exponent have to be exactly the same. So log base b of x, y is equal to log base b of x plus log base b of y. Oops, sorry. Alright, I don't expect you to do that in an exam. Once you get to theoretical mathematics, then yes. Well, a few times in calculus, which we look at proofs. But that's sort of like the formal way of proving that to be true. Okay, let's start using it then. Oh, actually no, let's look at another property first, and we'll just put them all together here. Next property, not going to take as long. We're just going to verify it by sort of like just numbers, just to verify it works for some numbers, and we'll keep on going. So property 2. Alright, so if there's a quotient, if we are dividing two numbers, all we really have to do is find a difference. And since I'm not going to mention this later, let me just mention one little thing here before. Property 1. Notice right here we have a product of two things. If you're multiplying two things together, all you have to do is add. Hey, we used to say add the exponents together, right? But now we have to say add the logs together. So these are just exponent rules in a different shape and form. So if you divide numbers, all you have to do is subtract the exponents. Remember, logs are technically exponents. Alright, so verify with some numbers here. So log base 2 of 32 divided by 4. Which would be basically log base 2 of 8. And anybody with an answer there? 3 is good. Okay. Let me do it the other way. Log base 2 of 32, subtract log base 2 of 4. And let's see if we get the same thing. What exponent do you put on 2 to give you 32? I heard 5. What exponent do you put on 2 to give you a 4? 2, and then subtract from the other gives you the exact same thing. Again, just verification of that. Okay, property number 3. Alright, if you take powers of powers, because that's kind of what's happening here, all you got to do is multiply the exponents. And that's what that rule is. It's coming from the exponent rule. So log base 2 of 4 to the 3rd power. If we do this and multiply it out, it gives you 64, and 2 to what power gives you 64? I go with 6. So then looking at it the other way here, how about if I multiply the 3 with the log base 2 of 4? And again, just one example, just to verify it works with one single number. And 3 multiplies, let's see, what number do you put on 2 to give you a 4? Would be a 2, and 2 times 3. There it is. It verifies with just numbers themselves. Alright, so how does this work? First of all, we're going to try to do something called expand logarithms, and then we're going to go backwards. We're going to try to combine logarithms together here. So first one here is the expand property. Expand using the properties of logs. So let's see, if we are multiplying, we add the logs. If we're dividing, we subtract the logs. And if we're taking powers, we multiply that number by the log. Alright, so let's go for it here. So log base 3 of 5a over b. And it says to expand, so I want to expand everything out. So here's what we do. First of all, we look at this little quotient right here. Since I have a division marker here, I'm going to say, you know what, I'm going to split this off into a subtraction now. So log base 3 of 5a, subtract log base 3 of b. So I got rid of the quotient. Now the question is, any multiplication inside the log do you see? Yeah, 5 and the a. Let's split that off as well. Split the 5 and the a off. Since multiplication, now we're going to add. So how about log base 3 of 5 plus log base 3 of a. And then we still have that little ending there, log base 3 of b. Alright, number 2. Here we go. And hopefully you tried it already here. So the division marker is right here. So log base 10 of x squared, hopefully. Subtract the remaining part. And we got some more stuff to do. How many, raise your hand if you went on. You saw that there's more stuff to do. Ah, look, those that did their homework from 8.1, 8.2, 8.3. Okay, rule number 3, or property number 3. Something about this little 2. Where should this 2 go? Should go right in the front here. So how about a... you know what I did actually beforehand? I wanted to do this right here. This little cube root right here, I need to change that into an exponent. What is cube root as an exponent? Anybody? Everybody okay with 1/3? Right? It's the index of the root becomes your denominator. Okay, and then that point is property number 3. Property number 3 says you whatever exponents you have inside the log, we put as multipliers outside the log. So 2 log base 10 of x, then minus, then that little 1/3 has to go over here. So 1/3 log base 10 of y. Ooh, quick here. How many got to that point? Raise your hand. 1, 2, 3, 4. Okay, 4. I think that's pretty much as tough as it gets on the homework here, so that should be fine. So this is expansion. We're trying to expand it out, making the variable or number inside the log as plain as we possibly can make it. Okay, let's go the other way though. Sometimes we'll see it as like this. We'll see it all laid out, and then one is going to bring it back together again as one single log here. Alright, so let's write this as a single log. Alright, so looking at this here, first things first, I'm going to take all my multipliers, this little 3 in front, and move it inside. So the way we'd have to do that, how about log base 4 of x now to the 3rd? That 3 has now become the exponent on the x. Nothing to do with the middle term, but this little 2 right over here. So that 2 has to now become the exponent on the z. So how about log base 4 of z squared? So move those inside. Now let's deal with the pluses and the minuses. There's my little plus right here. So now that becomes a multiplier. And you can do this all in one step. You don't have to do 2 steps to do it. Anything that's being subtracted, that goes down to the denominator. So now the z squared has to go to the denominator. So how about log base 4 of x cubed y on top and z squared in the denominator. Alright, and then the other portion, 8.4, how about let's try a logarithmic equation to solve. Let's see how we can do that here. Alright, of course, if you see something highlighted, that means the answer in the match problems answer sheet was wrong. Just have to keep on correcting the publisher again. I don't know. Alright, so let's go with solving a log equation. Ooh, that's kind of cool. First time we're getting to this part. So log base 2 of x plus 3 is being added with log base 2 of x equal to 2. We wanted to figure out what in the world is x. Alright, so let's go for it here. So first things first, this is why we practice this. I have to write this as a single logarithm because I really can't do anything with multiple logs inside my equation here. So see a plus sign, what should we do? We're going to multiply, yep. So log base 2 of, and then with the way the book writes it, I'll write it like this as well, just to sort of, you can see what the multiplication will be. It's going to be the multiplication of x plus 3 times x. And again, you can multiply it if you like. That's fine. Still equal to 2. So notice I got everything just in terms of just one log. Alright, so how do we solve log functions? What we're going to do is we're going to change forms. So this is the exponential, sorry, this is the logarithmic form. I want to change this into the exponential form. This will be fun. You ready? So what's my base? 2. What's my exponent? This 2 over here, right? That's going to be equal to whatever is inside the log. So just to make it look nice, I'm going to go this way. I'm going to say whatever is inside the log is equal to the base and the exponent. As long as we know where those numbers came from, we're good. The base came from log base 2, and this one came from here. Hey, so notice I got outside of the log function. Now I can solve this. I think I can solve this. Simplify both sides here. So this is going to be x times x, or x squared, x times 3, or 3x. This one's going to be 4 on that side. And what should we do? I think I'm going to subtract 4 from both sides, is that right? Set equal to 0. Something called factoring on our hands here. So I need two numbers, multiply to negative 4, add to a positive 3. I go with 4 and negative 1 maybe. Yep. Those are the factors, so there my solutions would be x is equal to negative 4 or x is equal to positive 1. Okay, the only problem is we have a small problem on our hands. And we have to go back just real quick because the book didn't talk about it quite well enough, I think. So let's see. Think about something called domain. What you guys think about domain? What numbers will or will not work inside a log function? Hold on. In terms of a graph here. So let me graph this function here. This was the exponential function we did, and then we graphed the logarithmic function. So remember exponential function. This is the red one. Can I plug in whatever number I like into an exponential function? If I plug in like negative 10, will that still give me an answer for y? Maybe. Exponential functions, they go from all the way from negative infinity to positive infinity, right? They stretch across the whole entire x-axis. My question to you, does the log function stretch across the whole entire x-axis? I don't think so, huh? If we take these red dots and convert them into inverses, take the blue dots, and we map them, notice what happens. It doesn't ever touch x equals 0. There's never a time you can have log of 0. You have to have log of a positive number. Good there? There's no such thing as log of a negative number. It does not exist. Let's see how else to say it here. So over here, if I look at these, I'm going to say to myself, you know, when I plug in a negative 4 back into this function here, do I get a negative anytime? Yeah, negative 4 plus 3 is negative 1, right? There's no such thing as negative 1. Doesn't happen. So that gets crossed out. Now, let me show you a little something here. If this was x plus 3 here, and let's say this was like x plus 5, I could accept a negative 2 as my answer. Does that make sense? It's not so much as the answers are negative, is that when I plug it back in, I'm not taking the log of a negative number. That's the problem.
So you can have positive numbers and plug it back in equals negative, then
Perfect. Good job. Yep. Even if you have positive numbers here, if you plug them back in, and you get a negative. So if this was x minus 3 over here, and you plug that 1 in, 1 minus 3, and that won't work either. Cool. So we, real quick here, if you want to write it down. So when you plug the numbers in, you have to take log of a positive number. Since a lot of you guys are looking dazed at me here, I don't know if it's too early in the morning or that didn't set in quite well here. Let's do some numbers here. Let's crunch some numbers just to make sure we understand this here. Let's go for it because it didn't seem like it sunk in. All right, write it down with me if you like, or don't write it down with me. But let's go for it here. So, what's the answer to this? Cool, I heard 5. I'm good to go. Yep, 5. Okay, what's the answer to this? What exponent do you put on 2 to give you an 8? Yeah, this all makes sense, right? We can take, and let me give you the exponential form. So we're saying this. We're saying, what exponent do you put on 2 to give you an 8? And that answer we just found out was 3, right? It all makes sense. What exponent do you put on 2 to give you a 32? And that makes sense that it's going to be a 5. Cool. Let's go down here. Is there any way for this to happen? What's that? What exponent do you put on 2 in order to give you a negative 8? Yeah, does not exist. There's no exponential form. What should you put here to give you this? You can't, because you can't take powers of positive numbers and somehow end up in a negative number. It doesn't make sense. So for logs, it doesn't make sense for you to have a negative number there. Alright. Also, it doesn't make sense for you even to have a 0 here. So let me try this one here. Is that even possible? What exponent do you put on 2 in order to give you 0? Again? 1? 2 to the 1 power is 2. 0. Let's try that one because that's a popular one. So we heard 2 to the 1, but that's 2. 2 to the 0 power. Anybody got that one?
1.
Oh, that's 1. That's not 0. I need a 0 here. It does not exist. It comes close. Remember, because if I do this here, if I do 2 to the, if I do the exponent, remember the exponent goes like this. This is 2 to the x. Remember how we talked about as the numbers become negative and negative, the x coordinates become negative. This guy gets closer and closer to 0. But does it ever touch 0? No, the graph never touches 0. So this is not possible. It has to be positive, some kind of positive number for this to somehow happen. Okay, does that make sense? Hope it made sense a little better. Let me jump back to the problem we were dealing with here, and let me run through the problem. So we changed forms, we've solved the equation itself, and after solving the equation we had to plug the numbers back in to make sure we're not taking logs of any zeros or negatives. Cool. So the -4 does not work. And real quick, because this is somewhat important here, the positive numbers won't work sometimes either, because when you plug it in, and if you subtract stuff from the positive number, that won't work because it would ruin the domain. You would have to be taking still a log of a negative, so kind of careful with that. Okay, with that said, x equals 1 is the final answer here. And let's jump to 8.5. Bless you. All right, let's go for it here. So there's actually two very special logs. These ones we use all the time. And remember how I told you mathematicians are really lazy? We don't write exponents on top of numbers, right? We don't say 3 to the 1. Right? We leave the 1 out, just we assume there's a 1 there. Well, there's two very logs that are used quite often here. The first one is something called the common log. Common log is when we think of the base being the 10. And so what we do, just like with exponents, we forget about writing it because we write it so often. So log, the 10 is missing now. So if there's no number there, we assume there's a 10 there. Assume that you're a common log, assume you are working with the base of 10. Alright, and then this little scale here. Why do one of the ways we use it, because many times we're thinking about decimal place value, because that's really what it's all about. Just like decimal place value is very important when we think of numbers here, log is interested in decimal place values. Also, the log button is actually on your calculator as well. You should see a little log button on your calculator. That log button is just the base of 10. No calculators have a log button other than base of 10, or the other one we're going to be talking about. Okay, so let's jump to it here. So use a calculator. Yes, you will need a calculator. Of course, those that didn't have a calculator, you went to the library and got one, the 3 of you. Otherwise, you downloaded one to your phone here. So I need to know, I need to calculate log of 27,600. So find the log button on your calculator somewhere. That's all you really need to do, and plug in the value. Alright, so calculator should look like this here, log of 27,600, and I got an answer of 4.44. So, I'm not sure why. On the book, it sort of varies how many decimal places it puts down. Sometimes it does 3, sometimes it does 4, and sometimes it does 2. And I'm not quite sure, there's no rhyme and reason for it. So as long as you're sort of close, you're doing good. So 4.409 is what the official answer is. Again, if you put 4.44, perfect. 4.4, perfect. Because the book never specifies exactly how many decimal places you need to have. Okay, don't need to write down the next part, but I just want you to think about this here. What does this actually mean? What does it mean to have an answer of 4.4404? That is this right here. It means that if you have a base of 10, if you take 10 to the power of 4.4409, you should get close. Maybe not exactly, but you're going to get close to 27,600. Good? If you want to try it, go ahead. Try it on your phone or something like that. Just put 10 to the power of 4.4409. and just see what it's going to come up to be. And anybody tell me what it came up to be. Is it exactly 27,600 or is it approximately?
27,599.
Cool, okay. It's going to be 27,599. Again, very close, just we need more accuracy on the decimal places. But that's kind of cool. We're finding out exponents, which we would never be able to do before, because we only work with integer exponents up until now. Okay, let's keep on going with it here. Next one, can you calculate log of 0.00391? And anybody tell me when you get it? He is going to be a negative number, and the reason for it, because it's a negative number, because it's actually smaller than 10. Actually, no, smaller than 1, that's why. Because remember, 10 to the 0 power, let me write this, yeah, 10 to the 0 power is 1, correct? So then anything that's less than 1, this number here now is going to be a negative. Okay. So I put it in, calculator negative 2.4078. That's fine. And again, if you're not getting any of these here, come talk to me during break here and I'll start to help you if there's something that doesn't look right on your calculator. Number 3, again one more time, something like that. All yours, log of 0.00952. Alright, plug in the calculator here, and that's what I got over here on the calculator itself, but about negative 2.021. I just put 4. If you want to put 3.6, absolutely fine by me. 0.02, that's fine as well, just as long as you are pretty close to that number. Okay, let's switch it around just a little bit here, as we talked about with number 1, the meaning of it. How about if you want to find out this? I want you to solve the equation of log of x equal to 3.9786. Go with that. Yep. All right, this one we're actually solving the equation, is that right? We're trying to figure, okay, hold on though. That is actually meaning this. Doesn't this mean this? It's the exponent already on 10. Right? So you're saying 10 to the exponent of 3.9786 equals what? Alright, hopefully plugged it into the calculator here. That's what you would have to do. Alright, 9,519. At this point I can just put in a whole number at this point. Okay, everybody good there with number 4? Tried it on your calculator as well. That's the whole point of this. Okay, and a little highlighter here. Again, that answer is not the same answer as in the answer to the match problems, but that's okay. Okay, number 5, still the same thing here. What's log of x equal to negative 1.5901? Okay, same thing here that we did for number 4. We change it into an exponential form, which is now 10 to the exponent of negative 1.5901, and that is equal to x. And now we get to plug that into the calculator. All right, anybody with an answer there?
0.257.
I go with that. X is approximately 0.0257. All right, let's take just a little bit more time extra here with number 4 and number 5 because I want you to show you something as well here. So now let's go back to the little chart that we were talking about. This chart right here. So what you should think about, log of 1,000. Log of 1,000 is 10 to the third power, right? So that means if you compute it here, log of 1,000 technically is 3. And then you kind of go from here. So that's what you should be sort of thinking about here. So if you're looking at any hundreds, if you're looking at log of 100, it should be 2. If you're looking at log of maybe like 200 or 300 or 400, then you know it should be about like 2.2, 2.3, somewhere in that range. As you get closer and closer to 1,000, let's say log of 958, then you're probably looking at about maybe like a 2.952 or something like that, somewhere in the 2.8, 2.9 range. So that's what we should think about with log. So log of 10, again, is 1. So that means if I had log of 15 or log of 25, I know it's about 1 point something. It's in the low ones. If I have log of 88, I know it's in the high 1 point something. Cool. So that's what we should think about. The other stuff here is log of 1 is 0. We already know that based upon properties. And again, anything less than 1, now if we go into decimals, now you got yourself negative numbers. So that's kind of what you should be thinking about. If it's a tenth, you should be thinking about a negative 1. If you're in the hundredths place of something, now you're talking about a negative 2. Again, if you're in the thousandths place of something, then you're talking about negative 3. So now let's bounce back to number 4, number 5. So does this make sense? We're going to get 3.9786. So it's almost 4, just shy of 4. And does 9,000 make sense? Yeah, because 10 to the 4th power then would be 10,000. Cool. All right, let's jump to this one. And now if you're talking about negative 1.5901, again, that ones place, it's a negative here, so it's negative and it's negative 1.5. So it's past the tenths place, right? It's getting closer to just 1/100th of something here. And then again, this one's a more difficult one. This is 0.02. It's 2/100ths, right? But it's not as low as 0.01. It's not quite there to that, just that one single 1/100th of a piece. So again, just for you to think about sort of the magnitudes there. Okay, but let's go back to our earthquake scenario. So in 8.3, we found that the magnitude m of an earthquake that produces a shock wave t times larger than the smallest one we can ever measure should be measured as a seismograph. Hey, look at that. First of all, look at that. From 8.2, we remember how we put that 10 in there all the time? The new formula, the shorthand way of writing it would be m is equal to log t. And we assume there's like a little 10 right over here. Okay. So let's go for it here. So find t. Oh no, how much, I guess, vibration or how much of a shock wave was made if the earthquake measured 5.5. Let's plug everything we know. So the m is 5.5, it's log, and then we just put t. All right, how do I solve this? I think we did that for number 4 and number 5, didn't we? We've got to convert it to a different type because the t is stuck inside the log. So if the t is stuck inside the log, let's go 10 to the 5.5 is equal to t. now we can use a calculator to solve that. Anybody with an answer here? Whew, we got 5.5, so that means we're in the what? I think it's going to be the 100,000s, is that right? We're in the 100,000s. I go with that here. On a calculator, 10 to the 5.5 gives me 316,227, 0.766, or we could just write 0.8. All right, and again, this is a scientific number here, so I gotta probably write it in scientific notation if this is gonna make sense. Can you write that number in scientific notation? Let's see. If in order for this number to be in scientific notation, the decimal would have to be where? Right after the 3. So it's going to be 3 point. And then again, maybe 1 or 1/6 or 1/62. Again, that's going to be dependent on how many significant digits you have. And we talk about that in science, not in math class. Times 10 to the, and then in my mind what I do is I go over here, I say to myself 1, 2, 3, 4, 5. Of course it's going to be 5 because 5 is over here anyway, right? We already did 10 to the 5. All right, good to go there. All right, and let's move on to another type of application here. And again, this was going into chemistry now. In chemistry, we have something called pH. And if you think about pH scale, we'll take a look at a graph here in just a little bit here. But that is really just the concentration of how many, it's called hydrogen ions, are in or present in something. Something like rain or battery fluid or lemon juice, whatever it is. So pH of something is really the negative or the opposite of the log of how many hydrogen ions in moles per liter. And again, you have to go to chemistry to figure out moles per liter. Anybody remember what moles per liter were in chemistry? No chemistry students here. Any chemistry majors here? Okay, I'll be worried if you don't know what moles per liter are and you're a chemistry major. Okay, so let me look at a graph here because take a look at a graph here. So we have is the pH scale. Here it is. Starting from, let's start from the neutral here. Neutral water, Plano water is about exactly at 7. If we're talking about our blood is slightly alkaline, so it's about 7.3, right in that range, 7.3. Anything beyond that, then you die. So we go from there. Anything that's more and more alkaline, and we get to the point of ammonia is right over here. Anybody smelled ammonia before? It doesn't smell very nice. Okay, and then you can actually even go further still, get more and more alkaline. The other road is to go acidic, and again, apple juice, there it is. There's acidity of apple juice. Vinegar is about right here. Lemon juice gets you more, and then you can even go to battery acid. So yes, you don't want to touch that with your fingers ever. Okay. Again, the more you go over here, the more you can dip your finger into something, and your finger is gone immediately. So when you get there. Anyways, this is called a pH scale. Let's kind of do a little bit of computation with it here. So find the concentration of the hydrogen ion in a can of cola. And we know that the pH is 4.1. So verifying if that is true. Alright, so let's go with it. It's 4.1, because that's the pH scale. And it's going to be negative log of my pH ions, or the H ions, hydrogen ions. Can I change it around? I think I've did this before. What do I change it around into? Got to do well, I guess we should do a little bit of work here. That little negative bugs me, right? Because we've never seen a negative before. So let's take the negative, put it on the other side. Negative, now it's a negative 4.1 log of hydrogen ions. Okay, now I can change it. What's my base? 10's the base, and how about a negative 4.1? And that will equal just the number of hydrogen ions in my mixture. Cool. Alright, and if you punch in a calculator, you're going to see some funny stuff happen, maybe. And tell me if your calculator does some funny stuff like this. It'll have like an E at the end, or it'll have this kind of like a squiggly sort of line there. Or it might just have straight numbers. It's just going to 7.94, something like that. Okay, all the way at the end, do you see like e to the negative 5 or some space? Okay, so you either have like 0.00000 and then 79432, or you have something that looks like this. It's called scientific notation already. Since we compute things in scientific notation, it's given to us in scientific notation. Alright, what does this mean? It means this. It's 7, well, let me rewrite it here. 7.94. 3e to the negative 5 really means this right here. It means 7.943 times 10 to the negative 5. So those of you that have a decimal answer, 0.0007943, you still have to convert that into a scientific notation answer. Alright, and then final answer here. So I guess the number of hydrogen ions would be approximately 7.9 times 10 to the negative 5. And again, I need units here, so it's going to be moles per liter. Okay. On number 8, normally we don't do this. Normally we don't go backwards. We don't say, oh, I already know what the pH scale is, and then I go backwards. That's not what happens. Normally we test something, and then we figure out what the pH is. Concentration of hydrogen ion in a sample of acid rain is 1.8 times 10 to the negative 5. So we put it into a little machine. It tells us how many hydrogen ions are there, and then we're going to convert that into a pH scale. Then we're going to say, hey, it's bad, or it's really bad, or it's okay, no problem. Alright, let's go for it here. So we're going to go formula the proper way to do it here. So pH is equal to a negative log of the number of hydrogen ions, and we already know what that is. So let's just plug it in. I like this when it's just pre-algebra. When it's just not algebra, I have to solve something here. So putting that into the mix there. Again, just like that if you like. Those of you that have a scientific calculator that does the order of operations for you, you can just plug it in just like that. If you don't, you got to do this first, and you got to do the exponent first. So you got to go 10 to the negative 5, whatever that is, times 1.8. Press the log button, and then take the negative of it. Again, if you have a scientific calculator, then you could just plug all that in right then and there, and then just get the answer, which what I got is a negative 4.1. 74427, blah blah blah. Plugs into the formula, that's about a 4.7 or negative 4.7, and the opposite of that would give you a positive 4.7. So real quick here, alkaline or acidic? Yeah, acidic and a little bit more the alkaline than apple juice, if you look back to the chart. Okay, so here are the it's the common log and the applications of the common log. Let's jump to another one here. Let's jump to something called the natural log. All right, so remember, we could put any any base we like on a log. Remember this one from 8.1? This was sort of like a little special exponent log. So it's used in nature. It just kind of fits the models we use. And so what we do is we say, you know what? If I can put in whatever base I want for the log, I'm going to put in log of e, log of the exponent. And what we do is we call it the natural log. And of course the question is, Mr. H, if we call it the natural log, why in the world do we put NL instead of LN? Is because when this was sort of first discovered and set in mathematical terms, the French did it, and we already know the French are always backwards, so we're good like that. No, in French they say log of the natural. That's what they say, log of the natural. So it just sort of stuck as just ln as abbreviation. So ln x or ln of x. Okay. First things first, since we have this new way of writing things, remember all those properties we have for logs? All those properties all hold. So let's do this here. This is not inside the textbook. I wish it was. Let's go back. Let's take a look at the properties that we have for the log, and then we'll convert those so it looks like ln. That's the first thing we got to do, or else it won't just not make sense. So what I did is I went to the review section for our chapter, and 8.3, we looked at these today, 8.3, and then all these little properties that we just learned today. Let's convert these into this little ln sort of phase. Cool. So I'll write them down. You can ask me any questions if you like. So if I'm going to put log base b, I know this is log base e. So this one right here, this property where you have base and the log and the exponent, now converts into e being the base, ln of x. And you guys tell me what the answer is. So let's take a look at this before I give you the answer. So this b here is technically this little e here, right? It's the x, it's the base now, right? This log of b, it's just log with the base of e. So these two will still cancel out. So notice it's the exponent here. It is what log is from. That becomes the answer, so this is just x. Does that make sense there? Just like this base b and the log b and the exponent, those canceled out. Same thing here, the e and the ln are going to cancel off. It's okay, we'll get there in just a bit here. That makes sense. Okay, number 2. Let's see. Log base b of b to the x is equal to x, therefore, well, how about ln of e to the x? What is that going to equal? Perfect. We're getting somewhere there. Yep. Just going to equal x because the ln and the e are going to cancel themselves out. Boom. Okay, and the properties that we learned today. Let's write this in terms of ln as opposed to log of b. If this is written in terms of ln, it would be, let's see, ln of xy, is that right? Is equal to, and you guys finish it off for me here, ln of x plus perfect ln of y. Okay, good there. We've converted a multiplication of the xy's to addition of the xy's. All right, you guys get 2 and 3. Can you rewrite it in terms of ln as opposed to log of b? All right, and I think most people are done here, so let's go with it. Check if you're right. Ln of x divided by y now becomes ln of x. Subtract ln of y. And the other one here, this becomes ln of x to the r. No need to put an e in here because it's not connected to the base anywhere. It's just the variable or the number to the exponent. And then that r goes out in front, so r ln of x. So those are all our properties just in terms of ln. Okay, we'll use those properties in a little while here. But before that, let's just get used to this whole concept of ln. Actually, no, we are going to use these properties here, so let's go for it. Maybe one more thing here. We've got two sort of special logs here. Anybody remember this one right here? What's the answer here? Log base b of 1. Answer is 0. Okay, convert that into the ln feature or notation here. Is this okay? All right, so we said ln of 1. That's what it is. Again, it's sort of like this. It's what exponent do you put on e to give you a 0? I'm sorry, what exponent do you put on e? Yeah, what exponent do you put on e to give you a 1? And it would be a 0. Okay, let's jump to these here then. So simplify each expression. ln e to the second. And we talked about it here. The answer is just 2, of course. All right, next one. Everybody okay with just a 4? Cool. And again, it's actually all the same property, huh? It's actually property number 2. So ln e to this is -2, and then ln of e to the x is just x, just the exponent on the e. They cancel. The question is, where does the ln and the e go? They cancel each other out, just like. Let me maybe go like this here. Just like this one canceled itself out. Because you have to say, remember, ln, this one's just going to be a 3, right? So let's look at the first one here. ln of e, what that's really saying is you're saying this, log base e of e to the second. And since these cancel themselves out, that means these will cancel themselves out. That means these will cancel themselves out. And you just get a 2. All right, expand. There's my little expand rule. Expand ln of p times e to the rt. All right, tried it already here. Let's just see if this makes sense here. So ln of p e rt, the multiplication is between the p and the e, is that right? So let's separate that with the plus now. So ln of p plus ln of e to the rt. Hey, I know a little something here. I know that ln and e are going to cancel themselves out. So this becomes ln of p plus rt. All right, number 11. Now this one's a little different what we've been used to here. So this really tests your knowledge of the properties. So here's what it's given. It's given that you do know ln of 5. ln of 5 is given as 1.6094. ln of 7 is given as 1.9459. So those two you are given. You're trying to simplify letter A based upon those two quantities, or somehow getting to those two quantities. So let's see, how do we go from 35 down to a 5 or 7? Just a multiply, right? Of course. 35 is 5 times 7. So ln of 35 really becomes ln of 5 times 7. What can we do with the multiplication of two numbers? Yeah, add them, right? Absolutely, add the ln of those numbers. So in this case, let's see, that means it's going to become ln of 5 plus ln of 7. Good there? Hey, we know what ln of 5 is. ln of 5 is 1.6094, and the ln of 7 is 1.9459. Alright, and can we add those together? Absolutely. Adding them together gives you a 3.5553. Cool. Good there. So notice you take the ln, you try to figure out how can I break it up into a 5 and a 7. How can I split them apart or expand them out so that I'm just getting the individual piece of 5 and 7, and then at that point finally be able to solve it. Okay, a little tricky one here. Let you guys try it yourself. And then on your mark it's at, let's see how I can figure that one out. ln of 0.2. There you go. Tell me if it's true. 0.2 is not the same thing as 1 divided by 5. It's 2/10 of a piece, which means a 1/10 and a 1/10. Doubled. Okay, based upon that, can you finish it off now? So ln of 1/5. All right, hopefully you did this here, because there's a quotient there. You're going to be subtracting here. So ln of 1 minus ln of 5. And this one we still know, right? ln of 1 is not 1. It's a 0, right? What exponent do you put on e to give you a 1 is going to be 0. The ln of 5 is given, so then we have to take the opposite, so negative 1.6094. All right, and one more. This one should be somewhat of an easy one here then. ln of 49. All right, now we've tried it already here. So ln of 49, that is easy. I believe that is ln of 7 to the second power. And whatever you want to do here, most likely, probably going to bring it out to the front as a multiplier, right? Remember the little exponent property? And then you can calculate ln of 7, which we know to be 1.9459, and then multiply by 2. And how about a 3.8918 as our final answer? And how many got that before I got it? Cool, okay, good. Yeah, let me actually do it that way here, yeah. Some people did this, and that's perfectly fine. You got it. This was 7 times 7. I did it as ln of 7 plus ln of 7. You really don't need the parentheses. I just sort of put them in there here. And yeah, you're going to get the same thing here. So 1.9459 plus another 1.9459, and it'll still give you the same exact answer. Good question there. All right, moving on to the last section in chapter 8, 8.6, and we get to the exponential equations here. We're going to be able to solve these things, just like we did with all the other functions. We learned how to add, subtract, multiply, divide, simplify, and then we did equations. Then we learned, or graph them as well. We did that with the quadratic functions. We did that with the polynomial functions. At the end, we started finally solving the equations. We did that with the rational functions. We did that with the radical functions. And now we're going to do this with the exponential functions as well as the logarithmic functions here. So finally came full circle with all these different functions. Okay. So investment here, just as an example here, we had $500 put into an account that pays 5% annual interest, compounded quarterly. Yes, we do have an equation for it. I think we looked at something like that before already. And the question is, how long is it going to take for my money to double? That's the little key issue. So now we're trying to solve an algebra equation. Remember, previously we just sort of plugged it into a calculator or something, we got the answer. But now I want to be able to see, okay, how long is it going to take to double my money? How long is it going to take to triple my money? How much money, if I put this much in, how much money will I have when I'm in age 70? That's kind of the questions that were. Or even better yet, if I want that much money at 70, how much should I start saving now with the interest involved and everything else? So that's the type of questions we're going to do. But let's look at a sort of generic equation. How would you like to do it in a generic equation? Then we're going to jump into our problem set here. So we have 5 to the x is equal to 12. That's our equation right there. It's called an exponential equation here, except the x is stuck as the exponent inside this problem. What we have to be able to do, we have to unstuck it. And so what we do is we put in a log on both sides. Just like high school algebra. Remember how we used to be able to cancel off the same bases on both sides? We do the same thing in reverse. We're going to actually put in a log on both sides. And what happens here is I get to do this property number 3. I get to take this x and now bring it out in front. And once I do that, voila, I am actually outside of the log now. Now I can just divide by 5, a log of 5, and I'm with my answer. That's kind of what we want. We want to somehow be able to get it solved for x. Okay, that was the easy generic equation here. Let's jump to our problem. And I'm going to go just a little bit faster here so we can finish up before break here. Okay, so again, we just have four problems really. They're a little bit long, but just 4 problems. Okay, here is our problem. 2 problems. First of all, I can't get 12 and 20 to be the same base. If they're both the base of 2, I got this. This was easy. The other problem I have is my variable is stuck right in the exponent. I can't get that outside of the exponent. I got to do something with it. And what I do is I fill in a log to both sides. So I'm going to take the log of this side and log of this side. Okay, once I do that, my little power rule says x plus 2 I can bring out in front as a multiplier as opposed to an exponent inside the log. So x plus 2 on the outside. Now you do need that parenthesis there, absolutely, because you're multiplying 2 things or 2 terms. All right, so simplifying each of the equations, each side of the equation here, I guess I'm going to have to multiply the log of 12. Both sides says this is x log of 12 plus 2 log of 12 is equal to log of 20. Does it kind of look like weird with letters and numbers all jumbled up together and logs that are inside equations? Kind of weird. Okay, so where's my variable? all the way on the left-hand side, right? So let's move everything over to get that x all by itself. What should we do first? Absolutely, I heard subtract. The 2 log 12, right? So I'm going to subtract this piece right here out. So 2 log 12, subtracted out goes over here, so I'm left with x log 12 equal to, looks like log 20, subtract 2 log 12. Everybody good there? One step, second step, x is being multiplied by log 12, let's divide. Log 12, log 12. Log of 20, subtract 2 log 12 divided by log 12. Have we solved for x? We have, huh? Technically, we have solved for this. We can leave it like this, which is sometimes done. You have two sort of options here. If it says find the exact value, you could pretty much leave it like this. But remember how we can sort of put things together? Let's talk about that. I'm going to talk about two things here. Putting things together and then also plug it into the calculator. Like this little 2 here, can I bring this and become the exponent on the 12? It's the power rule, right? I take the 2, put it in. So let's do that here. Let me rewrite it real quickly here, just the stuff we had before. And let's go with log of 20 minus log of 12 to the 2nd power. And again, you can skip a few steps if you like. You could have, instead of writing it this way, you could have actually written as log of 20 minus log of 144 over log of 12. Good there. All right, even more simplified, what can we do with the little minus sign over there? Yeah, we're going to divide. So it's going to be log of 20 divided by 144 divided by log of 12. And the question is, Mr. H, do I need to simplify the 20 over 144? If you're going to leave it as its final form, you want to simplify fractions, right? But the question to this problem says find the answer, and they want it as a decimal. So that's all they care about. So in your calculator, let's see if we could try this here. In your calculator, plug in either the top equation, this little top equation right here, or plug in this little bottom equation right here. So try that first. Hopefully you tried it in the calculator here. I'm going to give it to you both ways here. You could have done it like this, log parentheses 20 divided by 144. You got to close off this parenthesis if your calculator does a parenthesis, because you're closing off this log issue here. Alright, if your log does not have a parenthesis button that opens up right away, then you're in trouble. Because if you don't, then what's going to happen when you write this, you're going to wind up with something like this. It's going to be like this, log of 20 divided by 144. See how the parentheses, you have to have those parentheses in there. With parentheses, now you're keeping the 20 and the 44 as a ratio inside the log. Good there? That's one little issue that needs to be taken care of. So if you made that mistake, take care of that. And then over here, not anything issue, not another issue here besides that little fraction, or how does that work inside there? Okay. All right, and let me just do a little other thing here. Actually, let me write it underneath. Let me write it underneath here. So log of 20 over 144. If you did not include the parentheses, then that would be wrong. You'd have to put in parentheses. You have to start those parentheses and finish them in order to get this correct. Alright, the other way to do it is to write out what was on top. Remember the top form. top form now is a little complicated here because let me go back real quick here. On top you have two terms, right? You got the log 20 and you got the 2 log 12. Because you have both of those terms, you have this situation happening. If you do this, log 20 minus 2 log 12 divided by log 12, do you see where's the division? Yeah, you're just dividing right here, and that should just give you a minus 2 at the end because you're just dividing technically a 1, right? So if you have two terms, you got to put this little extra parenthesis here and extra parenthesis here because you're saying, okay, all that stuff on top is now going to be divided by log 12. All right. So in this any point, we get ourselves a negative 0.794. Okay, let's go on here. And again, it's 4 problems, but the problems are lengthy. Okay, so if you don't get one of these here, please ask me a break. What's happening here? How come you're not getting, especially if you're not getting it on your calculator? All right, let's jump to number 2. Now this is the business question here. How long will it take for $5,000 to double if it is invested in an account that pays 11% interest? It's compounded once a year. All right, gonna go a little faster here. All right, first things first, I gotta get a formula here. Formula comes all the way, I think, from 8.1. So this is the compound interest formula from 8.1. Einstein, remember, called it the 8th wonder of the world. All right, let's plug in what we need here. So if we're going to invest $5,000, what we want to gain is $10,000 at the end. So how about this? $10,000 at the end is gained from $5,000 in the beginning, and then we've got the 1 plus interest rate is 11%. So how about a 0.11? Remember, n is the number of compoundings per year. And if it says compounded once a year, then I know n is 1. And then 1 times t. All right, and we're trying to solve this. I guess we've got to simplify it first. The 10,000 is easy on the one side. The right-hand side is the one I need to simplify the most here. So let's see. How about, well, let's see. 0.11 divided by 1 is still 0.11, and 1 plus 0.11 is 1.11. And then 1 times t is just the t. I think that's simplified enough. I don't think I can simplify anymore. So now let's start some algebra here. Let's solving this here. First things first, let's maybe divide both sides by 5,000. I was just slowly trying to get that 1.11 to the t by itself. So 10,000 is equal to 5,000, and the remaining part, dividing both sides by 5,000, gets us a plain 02. That's right, we're doubling our money, is that right? So I think I'm pretty much done. There's nothing else I can do. I've simplified both sides, and I'm stuck because the t is in the exponent. That's why I'm stuck. Hey, I know. Put log on both sides, is that right? Let's put in a log on the left-hand side. Let's put in a log on the right-hand side. All right, what should we do with the t? Yeah, bring it out in front. That's cool. So log of t, log of 2 is equal to t log of 1.11. My t is a little bit off here. Let me fix it. How about that's a little better. Cool. Now what should I do to solve for t? Divide by log of 1.11, 1.11, and anybody got an answer via calculator? I can even turn it around. Let me write the formula here. So t is going to be log of 2 divided by log of 1.11. Plug it into the calculator here. You should get about 6.64. And again, in terms of years, so about 6.6 years. All right, about 6.6 years. Okay, this is why Einstein called it eighth wonder of the world, because it really takes, let's just say 7 years, okay, 7 years to double, but every 7 years it's going to double. So let's do this here, just again, freebie. Ready? So we start off with $5,000, right? 7 years later, this is year 0. 7 years later, we're at $10,000. We're good. 14 years later, how much money do we have? Oh yeah, there it is. That's the issue right here. We've gained $20,000 in 14 years, which is now 4 times as much as what we started with. So now wait another 7 years. Now what do we got? 40, and this doubling process. So how much interest did we learn in 7 years? We only earned $5,000 worth of interest, right? In these 7 years, now we've earned $20,000 worth of interest. That's the whole issue of compounding interest. So remember how I talked to you about if you can put in $15,000 when you're age 15, you sit there, you just have to live to age 70, and if you do, you will have about $1 million waiting for you. But it's this whole concept. It just needs time. As long as you have time to get you here. Most people start investing in money right about in their early 40s. And they're like, oh, I got to invest money. And that's usually the case. Again, life gets in the way, something called family, something called kids. Gets there, and then at age 40, when the kids are pretty much probably more grown up, then you're like, okay, now I got to think about what's happening with the rest of my life. So that's kind of what happens normally. But again, if you could do it at 15, that's cool. All right, let's jump to one little other small thing here. It's the fourth property, one last property we're going to deal with here. And we remember we said that there's 2 primarily logs that we deal with. There's the common log base 10, natural log base e, and your calculator only has those 2 buttons. If you noticed, there is not a string of buttons called log base 2, then log base 3, log base 4, log base 5. That'd be too many buttons on the calculator. Okay, so what we do is we have this little formula that says I can change any base to any base that I like. So log base a of x, all I got to do is I got to take log of the base I want of the original number and log base of the number base that I like of the old base, of the previous base. So writing in terms of ln, you could write ln of x divided by ln of a. And the x is the number inside the log. The a is the previous base. Or how about like this? Log of x, log of a. That's kind of what we're looking at. Any one of those 2 formulas. Why did I put both of them on there? Because both of them are on your calculator. You could either use the common log or you could use the ln. You're still going to get the same answer. And the reason is because it's just a ratio of the 2. You're trying to get a ratio of the 2. Just like 2/4. As a ratio is really the same thing as 1/2. 3/6, still 1/2. It doesn't matter. The numbers could be switched, or the numbers could be changed or different. But you're still going to get the same ratio of the 2. Okay, there's a proof in your textbook, which I thought was kind of cool. the proof in the textbook, the fact that you can take any number, we use that, and we use the proofs to get you to the formula that we want, which is, here's that. Cool. All right, let's try it. We're going to try it on a calculator here. Cool. So log base 6 of 14. I want to figure out what that is. Our calculator does not have a base button, so let's go for it here. So we're going to convert it. Convert it one of two ways. Let's go for it here. Log of 14, using the common log, log of 6. So plunging that in a calculator here, hopefully you guys get in the same thing here as 1.47, approximately 1.47. All right, and again, about 1.4729 or so. Alright, on the calculator you could also use the ln button. And again, that would be ln of 14 divided by ln of 6. Punching that in a calculator here, and of course you should get the same thing as well. So again, try it yourself just to make sure you get the same thing, same number. Doesn't matter which number you choose. So last problem here, number 4. Suppose the population in a small city is 32,000. Beginning of 1994, the city council assumes that the population size 2 years later can be estimated by the equation. Hey, there's that little e there. So approximately when will the city have a population of 75,000? And again, at that point you're talking about, hey, maybe we need a new power plant in the city, maybe we need to have an extra well, whatever it is. You're sort of figuring out what time would that be. So formula is already given, and all we need to figure out is this right here, p-value here, 75,000. Goes in for the p-value, 32,000 what we started with, and e to the 0.05t. What the book is not talking to you about is this little 0.05. This is something called a growth rate, and a growth rate is always in terms of percents. So you're saying, okay, the population is growing at about 5%. That's where they're sort of getting that 0.05. Anyways, let's solve it. Anybody know what to do first? Perfect. Divided by 32,000 on both sides. That will get that little e by itself. Alright, so let's see. Both sides are simplified as much as possible. The t is stuck in the exponent. What should we do? Cool. Okay, so kind of careful here. You don't want to put a log on both sides. You want a very specific log. Which one do I want? I want the ln log, because that's the only one that's going to undo this little e right here. So let's go ln of 2.34375 equal to ln of e to the 0.05t. Alright, we have some kind of property that we practiced. In fact, we can just cancel the ln and the e, right? And so the right hand side just becomes 0.05t. Alright, next. Alright, I got people staring at me. I'm thinking this is the problem right here, right? Mr. H, why did that happen? Why did that happen? Let's go for it. So let's jump back to right here, this little property, ln of e. Remember how these will cancel? That was the whole point here. Ln of e, they will undo each other. Work, that's property number 2, I believe. Property number 2. There it goes. Okay. So 0.05 on both sides, and then we get ourselves, sorry, I should stop here. Go ahead. Divided both sides by 0.05. So we have t equal to all of that. And now punch it in the calculator and tell me how many years do we need a new pump or a new well or a new power plant? I go with that, plugged in. So approximately 17 years we'll have to need to upgrade some infrastructure there somewhere.